And we're back in better than ever, still in 14-2, the gas laws. In the first podcast in this section, we introduced you to the idea of Boyle's law as the relationship between pressure and volume. They are inversely related. And then we also started talking about Charles's law, which is a relationship between the temperature and the volume of a gas. And what we found as we looked at Charles's law was that it is a direct relationship or a linear relationship. Let's go ahead and write that off to the side. Is a direct or linear relationship, simply meaning if you double the temperature, the volume will double. If you triple the temperature, the volume will triple, and so on and so forth. It is a direct relationship. As one increases, the other increases at the same rate. Now, the reasoning behind this, as we scroll down, is fairly simple. As you increase the temperature, the particle speed is going to increase. So increase in particle speed. As you increase in particle speed, they collide with the container walls with a greater force. And as they increase the force that they're pushing on the container walls, that's going to allow the volume to expand. It's going to push it out further and further, assuming that the container allows for the expansion. Now, if it doesn't, that's a different relationship, and we'll take a look at that in just a second. But as long as the volume can expand out, it will expand. And of course, on the other hand, if you decrease the temperature, you're going to be decreasing particle speed. It's going to collide with the container wall with less force. And in fact, what will end up happening is that the outside pressure is going to squeeze the volume down and allow the volume, and actually force the volume to decrease. All right. So there's the reasoning behind Charles's law. Now, one of the relationships that's interesting with volume and temperature is that as you extrapolate this red line, let me go ahead and switch this over to red to keep this consistent, is that it points back to 0 degrees Celsius. And in fact, if you were to take other gases, I'm going to use some different colors so we don't confuse it with our previous examples. Oh, let's go like this. Any gas, the relationship between the volume and the temperature will in fact be linear, and they will all point back to 0 degrees Celsius. Now, 0 Kelvin. Now, 0 Kelvin has never been achieved, but it is believed to be the coldest temperature possible. In fact, that is where 0 Kelvin came from, is the fact that as you extrapolate these lines, they all point back to a particular temperature. Now, the reason why we think that this is the coldest temperature is simply this. Once you get to that temperature, what would the volume of the gas be? The volume of the gas is going to be 0. Well, if you get colder than that, what would the volume of the gas be? Well, nothing. I mean, you can't get a volume to decrease beyond 0. Like if we extrapolate this line this way, you would have a negative volume, which is physically impossible. So we kind of think that that is going to be one of those universal laws or universal, we call the speed of light the universal speed limit, but this would be one of those boundaries that cannot be crossed. That in fact, under that temperature, nothing can exist, or nothing will exist under that temperature. So we call that 0 Kelvin absolute zero. All right. So it's just kind of an interesting sidebar to Charles's law. The main thing here is realizing that volume and temperature are directly related. All right, moving on. Let's take a look at Gay-Lussac's law. Now, he was also a Frenchman. He was slightly after Jacques Charles. And what he realized was that when you study and you look at pressure and volume, pressure and temperature are also directly related. So we can write this as pressure equals some constant B times the temperature, or you could rearrange this equation to say pressure divided by temperature remains constant. And if you look at this diagram, here's a container that is not allowed to expand. Unlike the previous law where you allowed the volume to expand, here we're not. So what's going to happen if you look at, we'll call this one number 1. Let me do this one in blue. If you notice, we have 300 Kelvin and the pressure is 100 kilopascals. So if I take my scenario number 1, pressure is 100 kilopascals and the temperature is going to be 300 Kelvin. And of course that is equal to 1 over 3 kilopascals per Kelvin. Now if you increase the temperature up to 600 Kelvin, we have now doubled the temperature. Notice the pressure also doubles with it. It goes up to 200 kilopascals. So if you plug that into the relationship, you have 200 kilopascals over 600 kelvins, and that also reduces down to 1 over 3 kilopascals per Kelvin. And so once again, the idea here is that the pressure divided by the temperature is going to remain constant, and in fact it does. Now what would the reasoning be behind this? Alright, well, it's going to follow something similar to the previous example, where as you increase the temperature, particle speed increases. So we have an increase in particle speed. Because the particles are moving faster, they collide more frequently. So we'll just say more collisions. And by definition, collisions are pressure, so you get a greater pressure. Now, of course, if the container can expand, that greater pressure will push out and in fact expand the volume. But in this case, we're not allowing it to do that, so the pressure simply increases. On the flip side of that, if you decrease the absolute temperature, the particle speed is going to decrease. You'll have fewer collisions, and therefore lower pressure by definition. Alright, so in this podcast we took a look and cleaned up Charles's law, the relationship between volume and temperature. We've also taken a look at Gay-Lussac's law, which is the relationship between pressure and temperature. In the next podcast, we're going to take a look at what's called Avogadro's law. It's a relationship between the amount of gas and the volume. And then we're also going to take a look at what's called the combined gas law. We'll see you next time.